Okay, here we're going to look at how we can design things to make them better at retaining or losing heat. First of all, the most common one tends to be the vacuum flask. We'll have a look at each bit in turn. They want you to know that heat cannot escape or get into the vacuum flask. Sometimes they'll talk about having a hot liquid inside or having a cold liquid inside. Right, first of all, they'll ask you to say why is the plastic cap there? And you need to say it is an insulator. They don't use a metal cap. It's an insulator. It's a poor conductor. It is actually probably the weakest part of this system, in that it does allow heat through much better than the other bits. The vacuum is basically where they suck out all of the air between two layers of glass. And by taking out all the air between two layers of glass, there are no particles there. So therefore, convection and conduction by the gas cannot take place there because there are no particles in there. And that's probably has the biggest impact on heat loss. The silvered surfaces as well. By having silver surfaces both inside and outside, it stops heat travelling through the glass as well. Obviously, the silver surfaces also are on glass, and glass is a poor conductor of heat, so we can say glass is an insulator as well. So that's essentially it. There'll be a question along the lines of what design features does the vacuum flask have to stop heat escaping or getting into it, and you can describe each of those in turn: the plastic cap, the vacuum, the silvered surfaces. They may also want to know about cooling fins. Lots of devices, including car engines or car radiators or even computer chips, will have things on it called cooling fins. Here I've got a diagram of let's imagine the central processor of your Xbox or PlayStation or even a computer will have loads and loads of current going through there, which produces a heating effect. And if you're not careful, the heat can get so much it can actually damage the computer chip or slow it down. So on top of computer chips, you'll find there's something called a heat sink, and the heat sink is designed like that. It tends to have a massive surface area. So those fins, when it's pointed towards a heat sink, those are fins, and those are metal that take away the heat. There's a huge surface area there, and of course the heat can then escape into the air and get away quickly. Sometimes what you have is you have a fan above it just to keep the whole thing cooled down. So the heatsink conducts heat away from the chip, and the air convects heat away, and it's got a massive surface area. The key features. Very often the question tends to be about animals' size, animals being evolved or having adaptations to make them particularly good at cooling or staying warm. So here, obviously, the larger the surface area, the quicker it cools down. But obviously, huge ears like that would be a big disadvantage in the North or South Pole. So they'd have very small ears. Another example would be African ears, elephant ears. Indian elephants tend to have much smaller ears than African elephant ears because the temperatures in Africa tend to be hotter. Is one thing you could say. Right, now how quickly heat travels from one place to another depends on the shape and size and type of material. They want you to know that, so you might want to make a card on that, and the materials the object is in contact with. And the final factor is the temperature difference between them. Okay, the temperature difference between them. So for example, if, let's imagine inside a house it was 100 degrees, obviously that'd be a disaster, and outside it'd be 5 degrees, the heat transfer there will be much, much quicker than say if it was 100 degrees and 98 degrees outside. Just a 2 degree difference will lead to a slow rate of heat transfer. The other thing they may ask you is about surface area to volume ratio. Now, I can't draw a 3D diagram here, so here we're going to just use a 2D sense, but it should really be 3D. And you can see if you've got a small object, then a sizable chunk of that object is in contact with the air. I quickly count up the squares, then I've got 14 squares in contact with the air compared to, say, 20 of the whole volume. So it's roughly 1 to 1. But if you look at, say, a much bigger object like that, you can see there I've got 46 squares in contact with it, but the vast majority of squares are not in contact with the air. Obviously, if it was a volume, you could imagine it's going to be a lot bigger there. And you can see the ratio there, surface area to volume, is about 1 to 3. In other words, the volume is 3 times bigger than the amount in contact with the air. In a volume, it would be 9 times bigger, because remember, because in volume you're going to go a lot further than that. It's going to have a lot of squares behind it. It's a cube. So so obviously the one at the top will cool down quicker than the one with the larger square, and this explains how, for example, big animals exist in the North Pole or whatever, because they have to be big in order to have that bigger ratio of volume to surface area. So they've got a large volume and a small surface area in comparison to it. Obviously the polar bear's got a massive surface area, say compared to a rabbit, but what you find is there's a lot more of the polar bear that is not in contact with the cold, as opposed to the rabbit, where a lot of it will be in contact with the cold. And that's it. That's everything you need to know about heat and the design of objects.